welcome to the House of ZK Radio, which is a focused podcast and media channel exploring everything ZK, zero knowledge. I'm Alice, host of House of ZK Radio and education lead at ZKM. Today I'm joined here with House of ZK co-host Pavel and our guest Alberto, who is head of ZK technologies at Telos. Thank you so much for being here today, Alberto. We're very excited to have you.
Thank you. Thank you for having me here.
Yes, thank you. I'm wondering if we can first start off with an introduction of yourself. How did you get involved in the Web3 space and focus specifically on ZK?
Now it's quite a while. It was 2017, and I was the CTO of a startup working with AI, and I almost finished the project, and one of my friend and former colleague told me, oh, there is this interesting crypto project that is looking for someone for lead the development, and so he started speaking about this crypto thing. At the time, I mean, I didn't know anything about this, and I immediately was excited, super excited, and I said, yeah, okay, let's try this. And I mean, as you can imagine, at that time, many people were around me were saying like, "Oh, are you sure? I mean, it's a proper job." I mean, yeah, don't worry. And so I started then, and and now I think it was exactly the right choice. I mean, I've been working on very interesting things so far, and let me say, focusing on SNARKs from the very beginning, and probably we can go more in details later.
Yeah, that sounds great. Wondering if we can speak a bit more about, it seems like you've been in this space for quite a few years now, more about any kinds of your predictions or your long-term vision for ZK. What do you see as kind of the developments that are still needed to enable more mainstream, wider adoption, or any other kinds of metrics that you believe we should use to measure our progress towards that long-term vision?
Yeah, that's an interesting question. I mean, from the very beginning, I saw the value of ZK and SNARKs, in particular for what regards scalability. I mean, one of the first things that I've been working on was Zendoo, let me say, a protocol for enabling on-chain scalability by having sidechains with fully trustless sidechain, so leveraging SNARKs and recursive SNARKs to, let me say, prove statements about the sidechain to the main chain. And now, probably, I mean, for sure, is much more common. You have layer 2s that are using ZK and recursive SNARKs in order to prove, let me say, the communication and have a fully trustless bridge. But I mean, at that time it was not exactly so clear. So let's say in these years, you can see how much progress has been done in terms of performances, the proving systems more in general, but still there is a lot of progress that needs to be done. And in particular, if you think about ZK and more in general about Web3, currently a lot of the use cases that are possible on Web 2 are not possible on Web 3. And the reason there are multiple reasons. And, but for many of them, ZK and SNARKs can be the answer to this limitation. So just to make an example, on Web 2, you have your user data that is, let me say, I would not say fully protected, but at least you decide to, let me say, who share your data. Currently, if you want to implement the same kind of application on Web3, you should share, you have to share your data with the rest of the world for the rest of your life. And obviously, this is not acceptable for many use cases, right? And so, and here ZK comes into play and enabling such a possibility. Because the on-chain logic, instead of, let me say, verifying statements on your data, looking at your data, so on-chain, the on-chain logic can verify statements of your data by just verifying a zero-knowledge proof, right? So these open up the possibility of many more use cases that currently are not possible on-chain. But these open up also a problem in terms of efficiency of ZK verification. So, and these, let me say, answer your question. What are the things that need to be solved, and what are the next things that needs to be solved? So this is one of the elements that I've been focusing on in the past months, and I think that we will discuss it later. But this doesn't, let me say, limit to user data protecting application. You can have a similar issue with layer 2s, where now you can see that there are layer 2s that are leveraging snarks, recursive snarks, and so you can have ZK EVM based rollups, for example, and this can be, let me say, a way for enhancing scalability with some trade-offs, obviously. And let's say, but again, proof verification is expensive because you're using, let me say, stateful resources for verifying stateless things. So verifying a zero-knowledge proof is a stateless verification. And instead, you're verifying it on chain using stateful resources. So it's expensive. And so again, for what regards the layer 2s, it's needed to verify this proof on chain, and these can become expensive. And so even aggregating or having a more efficient way, to verify ZK EVM proof and layer 2 proofs, it's something that is fundamental to be solved.
Got it. So we've made quite a lot of progress in terms of performance, in terms of development of new proof systems, in terms of, say, lowering proof costs, but there still needs to be more progress in expanding to maybe new use cases that currently aren't possible on chain. But with that comes the caveat of the efficiency that comes with proof verification.
Yeah.
Got it.
Yeah, that's correct, yes.
And relating to that, I'm wondering, at least on Telos' side and on your side, if there are any kinds of specific ways that Telos is kind of addressing the developer experience or the user experience that comes with ZK. Are there any specific kinds of tooling or any kinds of specific infrastructure that you guys are focusing on to ease that barrier to adoption?
Yeah, for sure. Let's say, as I was mentioning before, we have been working on how to make zero-knowledge proof verification efficient on chain. And in this context, we have a vision where the developer will be able to write his own, let me say, on-chain logic in a language, and using the same language for writing his private logic. So, and what does this mean? For example, the developer can use a ZK VM for proving the private logics, like, let me say, for example, risk 0 could be 1 or SP1. And so you can have the developer writing his logic, his private logic in Rust, and the same for the on-chain logic. And so you can leverage the ZK VM, and then, let's say, we designed the protocol in order to be able to verify and efficiently ZK VM proofs. And so this is one of the things that we have been focusing on. And I'm speaking about, for example, risk Clonky, this strange name that, let's say, is a risk 0 to Plonky to Goldie Bear proof wrapper. But probably we will go more details later.
Got it. And wanted to also hear more about maybe some of your predictions for ZK in the future. There's a lot of talk on this idea of the ZK endgame, but do you personally believe ZK will dominate in the future, or can we expect a combination of multiple types of cryptographic primitives? Right now, for example, like MPC, FHE are becoming more prevalent in the industry. Do you expect ZK dominating, or can we see maybe like a combination of all of these different kinds of tools in the future?
For sure, a combination, but for what regards scalability, I mean, more for the proof of computation. So, I mean, we speak about ZK, but let's say for when we speak about scalability, is more the proof of the computation that provides you the possibility to scale. And so I believe that in the future we will be seeing even more usage of, let me say, SNARKs in order to prove the computation, in order to scale the on-chain logic. And by the way, I mean, that's another thread of research that currently I'm working on, and I mean, I would be able to speak about it in the near future. But yes, for sure, answering to your question, I believe that we will see much more happening in the future, and the more we accelerate the proof computation and the higher level of utilization of ZK we will see in the industry for sure.
Absolutely. And going on into some of Telos's new developments on the ZK side, I know that you guys are currently working on SNARKtor, specifically protocol for decentralized recursive proof aggregation. Just on the topic of proof aggregation, which you briefly spoke about, we're seeing recursively, or like the act of recursively aggregating proofs becoming more common to reduce proof size, to lower verification costs. But I'm wondering if there are any kinds of drawbacks or limitations when it comes to proof aggregation. In what scenarios should an end user use proof aggregation, and when it shouldn't be used?
I mean, let's say, currently proof aggregation already made a lot of progress in terms of performances. So with the usage of starts and let me say having smaller fields and so on, I mean, this improved incredibly the performances of the aggregation. And these, let me say, introduce the possibility to implement protocols like, for example, SNARKtor, where you can leverage recursive proof aggregation in order to make zero-knowledge proof verification on-chain more efficient. I mean, and this was, let me say, the main goal of the protocol was to, let me say, make the proof aggregation more efficient, or better, proof verification more efficient on-chain, but also in a decentralized way. And why that's important is important because mainly, I mean, if you're making more efficient zero-knowledge proof verification, but you're doing it in a centralized way, and then you open up the possibility to many more use cases leveraging zero-knowledge, if the protocol is centralized, it will become a censorship threat to the whole network, because let me say, if many transactions are going to leverage ZK, this will become the issue. And so it's fundamental that the protocol that allows to enhance zero-knowledge proof verification is decentralized. And so this was one of our main goal for SNARKtor. That, let's say, it's based on recursive proof aggregation, but it's not only recursive proof aggregation, let's say.
Mm-hmm. So definitely also considering that decentralization component is also as critical. Mm-hmm. Got it. And I'm wondering, just for any kinds of members or like any kinds of audience members who aren't too familiar with SNARKtor, if you could provide maybe a walkthrough of the protocol when, say, a user submits a proof and an aggregation request? What happens next? What will they see on their end?
Yeah, for sure. So, okay, as we were saying before, there are two main kind of use cases where you have user data protecting applications that are leveraging zero knowledge, or, for example, layer 2's proofs. I mean, these are just two examples because the protocol is agnostic on the kind of proof. How does the protocol work? It introduces three kinds of actors that are schedulers, provers, and submitters. So the idea is to have, let me say, schedules on a constant time frame that are defining the job for the provers. So on which proof the provers has to work on. And the provers, so they are assigned to aggregate proofs, and they produce the aggregated proof, and then the schedulers, the next scheduler, will produce a new schedule considering the newly aggregated proof and the source proof that were aggregated, so by removing them from the queue. And so you can see it as an infinite loop where the proofs are coming into the protocol sent by the user. These fill up, let's say, the mempool, the proof mempool. And then you have the scheduler that constantly generate new schedules based on the current mempool. And so you can see this proof, let me say, growing. I mean, it's not probably the exact term. I mean, you can see a proof that is the result of aggregating many other proofs. And so you have also the time divided in slots, in epochs that are assigned to submitters. And at each epoch, a submitter is entitled to pick up one of these aggregated proof and submit it on chain. And so this aggregated proof speaks about many proofs. And so by including on chain this proof, all the applications that, let's say, relied on the zero knowledge proof that were aggregated within this aggregated proof that was submitted on chain, they can convince the on-chain smart contract about the fact that they had a valid proof. So let's make an example. There is an application that is a car rental application where I have to prove that I have a valid driving license, and you have another application that it's casino game application where the developer want to be, let's say, compliant and verify that all the users are over 18. So in the trivial way, you will have the smart contract on chain verifying directly the proofs. Instead, with SNARKtor, you can submit the aggregation request to the network, to the SNARKtor network. The aggregation, let me say, continues infinitely and pick up the two proofs, the driving license ones and the over 18 proof. And then at some point, a submitter pick up one aggregated proof, submit it on chain, and then the user will be able to submit his transaction now without any more the proof, but just with the reference to the aggregated proof that was submitted on chain. And let's say the public input of this aggregated proof that was submitted on chain, let me say, is a commitment of all the public inputs of the original proof. So he can demonstrate that he had a valid proof. And so, for example, he can demonstrate to the car rental on-chain logic that he had a valid driving license because the aggregated proof ensures that there was a proof that he had a valid driving license. And the same for the over 18 proof. And so in this way, the verification on chain is just one verification instead of two. Now you can see it, let me say, on a bigger scale, where many proofs can be aggregated and can be aggregated very efficiently. And here, let me say, I can mention about, for example, the fact that we have been working on making recursive proof aggregation also efficient on the baby bear field. That this is something that was very important, for example, for enabling the usage of, for example, risk zero, because the risk zero ZKVM, but not only, are working over the baby bear field. So in order to prevent having expensive wraps with simulating the arithmetic, instead of simulating the arithmetic, you can aggregate over directly over the same field. And this is something, let me say, it's an additional, let's say, optimization that we did. And yeah, this is very high level how the protocol works. But many other, let's say, improvements have been done. Like, for example, in the trivial way, you can imagine having the scheduler verifying each proof received, in primitive, I mean, before adding it to the mempool. Okay, this is a possibility, but this is going to limit the throughput. You can imagine having a single actor that needs to verify the whole zero knowledge proof verification throughput. So we know that in primitive is fast, but in any case, this would become the next bottleneck. So what we did to avoid this? Okay, first of all, why in the trivial way of solving this it is needed? Because if you don't do it, you risk to be DDoSed. So someone can flood the network with invalid proofs, and you have, let me say, the mempool that is full of invalid proofs, and you cannot, let me say, and you assign them, and you cannot assign them to the provers. So how we removed the need of verification, but at the same time prevented the DDoS attack. So now let's imagine that the only thing that the scheduler does is verifying that you have a balance, okay, the balance that you should have for paying for the fees of aggregation. Okay. Now the scheduler, as we discussed before, assigned to the provers, to a prover, 2 proofs to be aggregated. And so it's the prover now that is entitled to verify in primitive the validity of the proof before aggregating them. And what happens in case one of the proof is invalid? He can create a proof of invalidity. So what does it mean? So you can prove that a proof is invalid. In such a way, you can, let's say, trustlessly charge the user for the invalid proof, because such proof of invalidity will be part of the aggregation process along with all the other proofs. So what do we achieve in this way? The fact that you don't have to have a single actor like the scheduler that is required for verifying all the proofs and becoming the next bottleneck. Instead, you're spreading the load among all the provers, not only the load for aggregating, but even the load for verifying the proofs. And you're preventing the DDoS attack by creating the proof of invalidity. I mean, this is just one another detail. Sorry, maybe it was too more details, but I mean, another detail about the protocol.
I guess how I see it, that these the entity, the scheduler, acts
Yes.
similar to a block producer on different blockchains. Like they decide what proofs can go in which order. I guess in
Correct.
a common I guess like an issue arises in regards to the MEV. So the potential for a a scheduler to reorder transactions in a way where it can maybe potentially front run some transaction, like in DeFi operations, I guess, are there any protections against this type of like reordering or potentially like censorship of the schedulers, that potentially the schedulers don't include a specific proof to be then aggregated or sent to the provers to then be aggregated?
I understand. Okay, good question. Okay, how you can solve this? It depends on how you construct the public input of your proof. So instead of, let me say, having your public input, let me say, showing directly the data that the scheduler can use in order to, let me say, prioritize certain proofs instead of others, you can design your proof, for example, by, and it's just an example, by hashing the data, the real data, with some randomness. And then when you go on, and so this will be the public input. So the prover will not know what will be the actual data. So he cannot decide what to prioritize and what to not prioritize. And so in such a way, when then the proof gets aggregated, the aggregated proof goes on chain, is verified on chain, and only then you reveal let me say, when you're invoking your smart contract, you reveal the pre-image of the hash. And so, and this can be used on chain. Obviously, you will still have the problem on chain. If the chain has the MEV problem, I mean, it will still have it. But let me say, you can prevent to have it on the SNARKtor side in this way.
Mm-hmm. Yeah, and thank you, Alberto, for that very comprehensive walkthrough. And it's very interesting that there's also the option to create that proof of invalidity in addition to those validity proofs that are submitted, and kind of spreading that load for aggregating and verifying those proofs across the different provers. So really like that kind of design choice that you guys made. But in terms of the roles of those involved actors that are involved, we have the schedulers, the provers, the submitters, as you mentioned, wondering how all of those participants within the protocol are incentivized. Do you use a specific incentive scheme for all of these involved participants?
Yeah, for sure. I mean, this was another important part of the paper and the design phase, where, I mean, how can the protocol be decentralized if it doesn't have a proper incentive scheme? So this was one of the fundamental elements of the paper. So let's say there is a contrast. We created a sort of a contrast of interest between schedulers and provers. And so where the incentives have been designed in order to create a market for provers that compete each other and have the scheduler incentivized to pick up the more efficient, in terms of costs, provers, but also having, but not only more efficient, but also the more reliable provers. Because you don't want to have, let me say, you don't want to choose the most inexpensive prover, but let's say an unreliable prover, because this will create a damage for you as a block as a scheduler. Sorry. So the incentives are designed in a way that creates this contrast of interest between the prover and the schedulers, and also another important factor that has been taken into consideration for how to, let me say, split the fees is how to incentivize and let me say the bigger proofs. What do I mean? The proofs that are the result of aggregating more proofs. So that was another important element that we we paid a lot of attention while designing the incentives in order to, let me say, have these implicit incentive for the proof for the scheduler to incentive to aggregate to give priority to proofs that are bigger than others, and because these obviously will augment the throughput, and obviously this will be in benefit of the users. And a similar, let me say, mechanism is in place also for submitters that are incentivized to submit the proof as soon as possible, and they are incentivized to pick up the best proof, that is the one that provides more throughput for the protocol. So yeah, for sure there is an incentive scheme on this.
Got it. And was also curious to hear more about some of the design considerations and maybe any kinds of trade-offs that you experienced in terms of the overall architectural design for SNARKtor. So you mentioned previously that you're utilizing the Plonky 2 Goldie Bear as for optimization, and then I know that you guys have also implemented some precompiles, like with the Poseidon hash function. So wondering if you could walk us through some of the decision making behind some of the choices that you made regarding the architecture.
Yeah, sure. So as we want to open up the possibility of writing user data protecting application using ZK VMs, it was necessary to have a way of aggregating ZK VM proofs, not EVM, ZK VM proofs efficiently. And as I was saying before, most of them are working over the baby bear field. So this introduced the need for, let me say, extending Plonky 2 in order to not only work on Goldilocks, but also on baby bear. And so this required to introduce the fields, the primitives, but also all the gadgets and gates that are needed for having the recursion over the baby bear field. And as the protocol, the SNARKtor protocol, we said before, we have aggregation requests that are received by the schedulers. These aggregation requests require a Plonky 2 Goldie Bear proof, and that we call user proof. So we needed to convert, let me say, use this term, the RISC-0 proof received in a user proof. So we needed to write a verifier in circuit of a RISC-0 received, working directly over baby bear. In the first version, when we did our first prototype, we did the implementation simulating the arithmetic, as we were using directly Plonky 2, that, let me say, and then aggregating over Goldilocks. But then we decided to make it more efficient and having the wrapping happening directly on baby bear. So for just to make an example, we can wrap a RISC-0 receipt in around, on a regular laptop, in around 900 milliseconds, and aggregate in around 400 milliseconds two proofs. So these are, and consider that, for example, the wrapping of the RISC-0 proof can be done also on the user side. Another interesting experiment that we did was to, let's say, generate the RISC-0 proof directly on mobile, and in particular on an Android device. So we were able to generate RISC-0 proof directly on an Android device, and then you can imagine having the developer writing mobile applications that are able to generate, that are written in high-level language as Rust. They generate the proof directly in in their mobile device, and then this is sent over to SNARKtor that aggregates them over the same field, and this is very efficient. We did something very similar for the Polygon Hermez ZK EVM. And let me say, for what regards the Polygon Hermez proof, okay, first, we needed to have a way for, again, verifying efficiently or to generate efficiently a user proof starting from a Polygon Hermez ZK EVM proof. And instead of doing it, taking the flonk proof, I mean, as you probably know, most of the ZK EVM L2s are using Starks for proving the EVM execution, and then let's say they are when they are submitting on chain, in order to have a more efficient verification on chain, they are wrapping in flonk, for example. I mean, this is what the Hermez ZK EVM does. So, and this wrap is very, let me say, computationally expensive. It takes a quite important portion of the time that is needed globally for generating a ZK EVM proof. So instead of wrapping this flonk proof, we also wrote the pill Stark verifier. So the Polygon Hermez proof, let me say, uses pill, and so the pill language, and so we plunked it to Goldiver, pill Stark verifier. So we were able to, without simulating any arithmetic and directly verifying the Stark proof, the batch proof, to create a user proof. So we have two advantages: no need for simulating the arithmetic and let me say, expensive change of proof system, and but at the same time avoiding the ZK EVM to generating the flonk proof. In such a way, you achieve these two results, or let's say in one, and having then aggregating the ZK EVM proofs efficiently, and then ending up on chain with one just unique proof.
Got it, and it's really great to hear kind of all these advantages of the use for these wrappers, both on these reserved proofs and then also the Polygon Hermez ZK EVM, and how you're able to have that balance for that pill Stark verifier. No need for kind of simulating those arithmetic operations, these expensive changes that come from the proof system, while also avoiding the ZK EVM itself for generating that flonk proof. So really great to hear that kind of balance that you guys provide.
Thank you. Mm-hmm. And this is also valid. I mean, I was just saying that you're not requiring, I mean, if you're aggregating, for example, 100 ZK EVM L2s, all of them can save the computation of wrapping in flonk. Okay, so it's not just one saving, it's multiplied for all of the, let me say, L2s that are being aggregated.
Absolutely, got it. And on the compatibility and also on the integration side, I'm curious to hear the types of proving systems that SNARKtor can be integrated with, and what kinds of benefits they'll provide there. And also was wondering if there are any kinds of plans for integrating SNARKtor outside of the Telos ecosystem.
Okay, for what regards SNARKtor is agnostic, the protocol itself is agnostic to the underlying chain. So you can see schedulers taken from the block producer. So in order to achieve or to inherit at some sort the same assumptions, you can, if you restrict the schedulers to a subset, I mean, it could be all of them, but let's say a subset of the block producers, then you can inherit some of the assumptions, right? And so, and this can be done on different chains. It's not needed to be only on Telos. I mean, it can be done also on other chains. So most of the components are going to be exactly the same if they are deployed on another network. And for what regards the proof system, as I mentioned, currently we wrote the Risk-Clunky wrapper, the Polygon Hermits one, and I mean, we will be extending, let me say, the possibility of wrapping other proofs. So, I mean, this is something that is an ongoing process that we have.
Got it. And I know that you guys also recently announced that you're in the midst of a development of a hardware accelerated zkEVM L2. So wondering about kind of the future next steps and plans going towards that direction. So kind of the motivation behind co-designing and also optimizing on the hardware acceleration side, and also wondering about some of the specific capabilities present within SNARKtor that are able to enable hardware acceleration as well.
Let's say, for what regards the zkEVM, it currently is deployed on testnet and is leveraging hardware acceleration on FPGA. And what we are working is also to hardware accelerate, let me say, the SNARKtor parts, so the proof aggregation. And this, let me say, is part of a bigger vision. I mentioned before, there are other threads of research that currently I'm working on, and the hardware acceleration of proof aggregation is for sure one important piece in this puzzle. And because the reality is that if let me say, currently the cost of proving, or better, the proving inefficiency of a computation, if the aggregation becoming expensive, the ratio, let me say, it can become, let me say, more feasible because you can parallelize the computation. But I mean, that's another totally different thread of research that we're currently working on. But I mean, going back to your question, yes, we are extending the hardware acceleration also for Plonky to Goldbeer and for having more efficient proof aggregation.
Got it. And just as a kind of last question before we close, are there any kinds of final thoughts or perhaps any advice to the audience that you'd like to make, or any kinds of like additional announcements, next steps that the team is thinking of? So I know that you said that one of your kind of focuses right now is hardware acceleration for proof generation, and then also with the Plonky 2 Goldbeer, any kinds of next steps that the team is planning on, or any kinds of closing thoughts that you have?
Okay, we're going to, let me say, progressively release open source all the libraries involved. So this is something that is going to happen in the next weeks. So, I mean, there are several libraries that currently we have developed in these months, and they are going to be published open source soon. And yes, I mean, that's one of the aspects, and the acceleration you just mentioned. And let me say, and we're working also on another protocol, and this is something that, I mean, it's not yet ready to be discussed today.
Right, sounds great. And thank you so much, Alberto, again, for joining us. Really enjoyed hearing all of the kinds of design considerations, choices in regards to the optimizations, like with your use of wrappers, and then also some libraries as well for SNARKtor. And then also, like, it was great to hear all of the kinds of interactions between all of those components, all of those participants within SNARKtor as well. So really enjoyed this kind of deep dive into SNARKtor, and hope that you can join us again sometime
Yeah,
soon
for
in the
sure.
future.
Thank you
Yeah,
very
thank you
much
so
for
much,
this.
Alberto.
Thank you, Pavel, and thank you, everybody.
Yeah, thank you so much.